welcome to another module in this massive open online course. So, today let us look at the power of an AM signal. Power of amplitude modulated, that is the AM signal, and we know that a typical AM signal is given as ST or XT. Let us use the notation XT. XT equals A cosine, or basically AC 1 plus KMT into cosine 2 pi FCT, which is the carrier component AC cosine 2 pi FCT plus the message component, that is AA AC, that is a carrier modulated with the message, that is AC KA MT cosine 2 pi FC of t, correct. Now, this is the pure carrier component, correct, and this is carrier modulated So, we have two components, one is the pure carrier AC cosine 2 pi FCT and the other is the carrier modulated by the message, that is your KA AC MT cosine 2 pi FCT. Okay. So, let us now to compute the power of the AM signal, that is XT, let us compute the power of each of these components separately and add them to get the power of the AM signal. So, we compute power of each of these two components, compute power of each component separately. Okay. Now, the power of the carrier, well, that is straightforward, we already know this thing, this is a sinusoidal signal. So, the power of this that is AC cosine 2 pi FCT is the amplitude square, that is half AC square. So, the power of the carrier, correct, the power of the carrier component, we already know that is a sinusoidal, that is a pure carrier, that is a sinusoidal signal. So, the power is half amplitude square, that is half AC square. Let us now compute the power in the carrier that is modulated by the message. So, now consider the other component, that is KACMT cosine 2 pi FCT. Now, you can think of this as the carrier and this as the amplitude, that is you can think of this, although this is not exactly correct, you can think of this as sinusoid with amplitude, that is I am writing using the approximate signs, sinusoid with amplitude Ka AC MT. Well, correct, although strictly speaking that is not true, because when you multiply MT, a time varying signal MT, correct, with a sinusoid, it is no longer a sinusoid. But since MT, message signal is varying much, because the carrier frequency Fc is much higher than Fm, that is the maximum frequency component of the message. Therefore, Mt, that is this envelope or this amplitude of this sinusoid, this Mt is slowly much varying at a much slower rate than the sinusoid, correct, cosine 2 pi f c t. One can approximately think of this as the sinusoid cosine 2 pi f c t with instantaneous amplitude given as k a c m t. And this, so let us write this justification also, since this is not always true, this approximation is valid since m t is varying at a much lower rate than cosine 2 pi f c t, that is your f c is much greater than f m, that we already know, alright. The carrier frequency is much greater than the message frequency. Therefore, the power of this can be instantaneous power, again can be approximated as half this amplitude square, that is half k a square a c square m square t. This is the instantaneous power, and therefore, average power from this, your average power can be obtained, the average power can be obtained as that is expected value of this quantity half, that is the average. Remember, E stands for the expected value of a random variable or a random process. In this case, MT is a time varying signal, so it is a random process. E stands for expected, this is the expectation or the average at the average value, and therefore, this is equal to, I can bring the constants outside, half k a square a c square average value of the quantity m square t. But now realize average value of this quantity m square t is nothing but the power of the message signal. We can denote this by the quantity p m. Okay. So, this average quantity, this is nothing but the power, expected value of therefore, let us say this is denoted by p m. So, this is half k a square a c square p m, where p m is the power of the, this is the power of your message signal, where p m is the power of the message signal m t. Alright. So, we have derived the power in the pure carrier component, and now we have derived the power in the component, that is the carrier, which is modulated by the message m t, and we are saying that power is approximately half k a square a c square into p m, where p m is the power of the modulating signal, that is the message signal m t. And therefore, now the total power is the sum of these two powers, the total power of your AM signal equals half AC square plus half Ka square AC square into Pm. This is the total power. This is the total power of the AM signal, that is half AC square plus half Ka square AC square into Pm. Okay. So, this is the total power of the AM signal. Now, let us define another quantity, that is the efficiency. The efficiency of this AM signal is basically the power in the message signal divided by the total power, that is the power in the carrier plus power in the carrier modulated by the message divided by the power in the pure carrier plus divided by the total power, right. Because remember, the useful part of the amplitude, the AM signal, amplitude modulated signal, is the part that corresponds to the carrier modulated by the message, because that is the actual component that is carrying the message signal, which is conveying the information. The pure carrier is only being transmitted to enable envelope detection, alright. Otherwise, by itself it does not convey any information. Therefore, the efficiency of this scheme can be denoted by the power in the message component, that is power in the carrier modulated by the message divided by the total power of the AM signal. Okay. So, the power eta equal to efficiency of AM, and this is equal to power, that is power in carrier modulated by message divided by the total power, and this is because, remember the justification, this is because the pure carrier component which is AC cosine 2 pi FCT does not convey any information. This does not convey any. The information is contained in the message signal empty. Therefore, the pure carrier is only being transmitted for envelope, to enable envelope detection, alright. That is the reason why the carrier component is being transmitted, alright. So, you will realize that if there is no information, why is being transmitted? The pure carrier is being transmitted simply to enable envelope detection at the receiver, and therefore, eta, that is the efficiency, is the power in the carrier, that is carrier modulated by the message, that is half AC square Ka square Pm divided by half AC square plus half AC square Ka square Pm, which is basically, that is eta equals, well, that is you are cancelling AC square, this is Ka square Pm, remember Ka is the sensitivity, Pm is the power in the message signal divided by 1 plus Ka square Pm. So, this is the efficiency of the AM system, correct. So, I can write this as the efficiency this is the efficiency of the amplitude modulated system, that is Ka square into Pm divided by 1 plus Ka square Pm, where Ka is the sensitivity and Pm is the power of the message signal. Let us try to compute this efficiency for a sinusoidal message signal. Consider now the specific case of a sinusoidal message signal. Consider a sinusoidal message signal Mt equals Am. This is our message signal with amplitude Am cosine 2 pi fmt, all right. Therefore, this implies that the power of the message signal Pm equals half Am square. This is the power of the message signal. Also realize that mu, the modulation index, equals, remember modulation index, this is defined, we have defined the modulation index, and the modulation index for this sinusoidal signal is basically mu equals Ka times Am. Basically we have defined mu in one of the earlier modules, and we have shown that for a sinusoidal modulation, for a sinusoidal message signal, mu equals Ka times Am, correct. And therefore, now we can also write half, correct, mu square equals half Ka square Am square, but half Am square equals Pm. So, this is equal to Ka square into Pm, which means the efficiency eta, of the Am signal, correct, for the sinusoidal modulating signal, that is, remember that is half Ka, remember that is Ka square Pm, which is now I can write this half mu square divided by, or let me just write it completely, this is Ka square Pm divided by 1 plus Ka square Pm, which now for the sinusoidal modulating signal is half mu square. Well, Ka square we have just shown that half mu square equals Ka square Pm. So, this is half mu square divided by 1 plus half mu square, this is equal to, well, mu square divided by 2 plus mu square, and this is another important relation of the efficiency of amplitude modulation for a sinusoidal modulating signal, correct. This is the expression for efficiency of Am for a efficiency of Am specifically for a sinusoidal modulation, where mu is the modulation index. This is specifically the efficiency of a sinusoidal modulating signal, where mu is the modulation index, all right, correct. And also now realize that if you look at this expression eta, again look at this expression eta equals mu square divided by 2 plus mu square. I can write this as 1 minus 2 over 2 plus mu square. Look at this, 2 over 2 plus mu square, this is decreasing with mu, and therefore 1 minus 2 over 2 plus mu square, this whole thing is increasing So, I can write the efficiency eta as 1 minus 2 over 2 plus mu square. 2 over 2 plus mu square is decreasing with mu, as mu increases this quantity is decreasing. Therefore, 1 minus 2 over 2 plus mu square is increasing with mu, which means as mu increases, the efficiency eta of the modulating of the AM signal improves, correct. So, now you observe this implies as mu increases, efficiency eta of AM signal increases. This is important to remember, as mu increases, the efficiency increases. Now, however, interestingly, mu, remember, for envelope detection, the modulation index mu has to be less than or equal to 1. If mu is greater than 1, the signal becomes over modulated. Therefore, for envelope detection, mu has to be the maximum value of mu can take is 1. For envelope detection, envelope detection, maximum value of mu equals 1. Otherwise, if mu is greater than 1, then the carrier lead becomes over modulated, correct, and this leads to envelope distortion, remember, correct. Since if mu is greater than 1, carrier is over modulated. This is termed as over modulated, which results in envelope distortion. Carrier becomes over modulated, this results in envelope distortion. Put these two things together, now you can see that efficiency is increasing with mu, maximum value of mu is equal to 1 for envelope detection. Therefore, maximum efficiency occurs for mu equal to 1, the maximum efficiency occurs which means eta max equals mu square by 2 plus mu square evaluated at mu equal to 1, which is 1 by 2 plus 1, which is 1 over 3. All right. So, this is eta max, maximum efficiency of AM with envelope detection, if envelope detection has to be allowed. Therefore, maximum efficiency of AM with no envelope distortion equals 1 by 3 or only 33%, which is a very surprising result, and this tells us that the efficiency of amplitude modulation is very poor, that the maximum efficiency that is possible is only 33%, which means close to 67% of the energy is basically wasted, correct. So, this is very poor efficiency, and realize that this is arising because we want to enable envelope detection at the receiver, for which purposes we are transmitting the pure carrier. So, the efficiency can be improved, but that means the power of the carrier can be should be decreased, or the carrier should not be transmitted altogether, and that is what we will discover in subsequent techniques of amplitude modulation, that is double sideband suppressed carrier, etc. So, therefore, to conclude, this efficiency is very poor to improve efficiency, that is 66% or 67% of power is wasted. Therefore, now efficiency can be improved by reducing the power of the carrier or suppressing power of the carrier. Energy can be improved or reducing power of carrier or suppressing the carrier. So, the energy can be improved by reducing the power of the carrier or suppressing the power of the carrier. This is what we are going to look at in the subsequent techniques, that is when we look at DSB-SC, double sideband suppressed carrier, that has a much higher efficiency because the carrier is suppressed, there is no power is wasted on transmitting the pure carrier. Alright. So, in this module we calculated the power of an AM signal, the power efficiency, and also the maximum power efficiency with amplitude with envelope detection. We have seen that since modulation index mu is less than or equal to 1, the maximum efficiency possible is 33%. So, let us stop here.